Hello? All right. Hi, everyone. I'm Leo, and today I'm going to be talking about what it takes to build a distributed system for the logistics industry. So, to set the stage, do you ever wonder where you get all your stuff? Your phone, your food, the chair that you're sitting on? Well, the answer is the supply chain. You get your stuff from the supply chain. Now, the supply chain is a vast, huge thing that it's difficult to grasp all at once. And we're just going to talk about a specific portion of the supply chain today, which is trucking, right? Trucks are used to move stuff from a mine into a manufacturing facility, into a distribution center, perhaps into a port, eventually to a household. And I spent most of my career in e-commerce, which focuses on the last mile to the household from the distribution center. And I never really knew what the supply chain behind the scenes looked like. But it's a very interesting thing, and let me share some numbers with you guys. So this is a look at the trucking market in the US. There are 1.7 million trucks in the US. There are 400,000 trucking companies, and they're sometimes called motor carriers, freight carriers, truckers. Together, those companies move $12 trillion worth of goods every year. Not billion, trillion dollars. The overall supply chain in the US moves around 15 trillion, 12 trillion is by truck. Now, here's some of the challenges with this. The trucking market is very fragmented. So that means that there's a whole bunch of very small trucking companies. Here are some stats. 90% of carriers have fewer than 5 trucks. And 99% of carriers have fewer than 50 trucks. 99.9% of carriers have fewer than 400 trucks. There are a few mega carriers out there, so you can think about Walmart, Amazon, UPS, but 99.9% of carriers have fewer than 400 trucks. Now, together, these carriers with fewer than 400 trucks make up 85% of overall trucking capacity, right? So on the one hand, that means that 15% of capacity is provided by those tiny number of mega carriers. But the rest of these carriers are pretty small, and they make up 80% of overall truck capacity. Now, just to give you a better idea, the players in this market are the carriers, these trucking companies. Then there's these companies called freight brokerages that exist in between the carrier and the shipper. Part of the reason they exist is because the carrier market is so fragmented, and it's difficult for shippers to do business with all these little carriers. Now, I didn't put this number up there because it's not really the core point of the talk, but another thing you should keep in mind is the carbon footprint of a truck. An average truck in the United States drives 120,000 miles every year and emits over 200 tons of carbon dioxide into the atmosphere. All right? So these are some numbers about the trucking market in the US. So what's the problem? What's the problem? Well, one of the problems is that these trucking companies with fewer than 400 trucks, they've been overlooked by technology companies. They don't have any technology to do what they're doing other than Excel spreadsheets. And if you spend some time observing how a trucking company works today, you'll see that if a company is big enough in size, let's say they have 100 trucks, well, they need to have a whole team to operate this business. Because they don't have automation technology beyond Excel, these smaller carriers, they miss more opportunities than the larger carriers. They make more mistakes. They drive more empty miles, right? More empty miles, which eventually, among other things, contributes to the carbon footprint. And so we're not really sure why it is the way that it is. I was really surprised to find out that there's nothing really out there for these trucking companies. Now, of course, Amazon, Walmart, they have their own platforms to operate their trucks, but of course, they're not sharing it with anybody else. And so this is the problem, is that we have all these trucking companies making up 85% of trucking capacity, and they only have Excel spreadsheets. And so that's the problem. I was pretty shocked to see it, but the good thing is we don't really need much to really address this problem. So once again, to illustrate a day in the life of a carrier, right? So if you're a carrier, maybe you're a dispatcher, maybe you're a driver. If you're a dispatcher, you're coming into the office in the morning, you get your coffee, and then you sit down on the computer and you start doing all these three things in parallel. You're sourcing, which means that you're looking for new loads. So you're going on all these load boards, you're refreshing, maybe making a phone call. And you're trying to plan the week, right? As a dispatcher, you usually have a team of drivers that you work with, and you're trying to keep them loaded. At the same time, you're taking care of fulfillment, meaning you're making sure that the loads that you already have are getting delivered on time. And this is an easy thing to do for the carrier, right? They have to know where the driver is, where they're going next, if there's any other trucks available. And then, of course, while doing all this, you have to manage the fleet. You have to make sure everyone gets paid on time. And here are the problems that appear when there's a disconnect between these departments. Is that if there's a disconnect between sourcing and fulfillment, you're going to be missing opportunities. You're going to be driving empty miles. There's going to be lack of visibility. Customers aren't going to know when you're going to be ready to take the new load. Similarly, if there's a problem between sourcing and management, right, it could be that you'll have a driver quit. They get a pay statement. They feel like they're being underpaid. Drivers are in high demand right now. Driver turnover is over 100% in the US. Drivers are scarce, and so you have to work real hard to keep them happy. Well, how do you keep them happy? Well, you pay them on time, you pay them the right amount. But it's hard to do when you have to rely on Excel as a source of truth. And in a similar sense, problems between management and fulfillment lead to accounting errors, perhaps overstaffing, and all these things will make a company fail. The margins are very thin for these carriers, and in order to really survive as a company, it's not just about buying a truck and moving loads on time. You have to take care of your operational workflows and automate them as much as possible. So this is sort of the stage that we're in. And let me introduce what we're doing about it. So I'm the CTO at Albus. I'm the engineer at Albus. And Albus is a technology company that's building a carrier operating system. And I'll tell you a bit more about what that is. Our mission is to improve the efficiency of supply chains in the United States at first, and then throughout the whole world. The company was founded by Nick Darman, who's actually native to Moldova, and then I joined as the tech guy to help us reach our goals. So here we are. Now, how do we actually build, right? And so the things that I want to touch on, there's obviously a lot that goes into building this sort of platform, and all of this should seem very, very familiar to everyone. This isn't anything new. But one of the parts I wanted to focus on is this last piece, operations and maintenance, right? And I want to talk about some of the challenges involved in building a distributed system and some of the approaches that we take to addressing those challenges, right? And so, again, the software development lifecycle is like it is at pretty much any other company. We do discovery, then we produce what we call an RFC, a request for comment, then we break that down into stories and tasks, so on and so forth. There's a technical design review, there's the development process, obviously we iterate. Now, because we have such a complicated, mission-critical system, we can't lose any data. Our customers rely on our platform every day to run their business, and customers in freight are very, very demanding. And so we can't leave certain things overlooked. We have to have strict guidelines for writing code, for designing the data model, for designing the data architecture, and strict guidelines for operations. Meaning, once you release a feature, the day isn't over. And I recently wrote a little post on LinkedIn about how back in the 90s, the Microsoft Word team went on a 2-week vacation after releasing the latest version of Word, right? Of course, for internet-based services, we can't do that, right? And when you release a feature, that's really when it only starts. And the production operation is going to be the best guideline for you to decide what the architecture should be, where the decomposition boundaries are. There's no amount of architecting on the whiteboard that's going to prepare you for what goes on in production. And you have to have a serious approach to production operation in order to offer a reliable service. So what is a distributed system? What are the challenges involved in a distributed system? Now, of course, there's lots of definitions. This is a bit of a comical one from Leslie Lamport, who's, of course, in many senses, the father of distributed computing. And he said that a distributed system is one in which the failure of a computer you didn't even know existed will render your own computer unusable, right? So here's the takeaway. Here's one of the aspects to take away from this, which is that a distributed system consists of multiple independent parts that aren't directly aware of each other. And that's a very, very different environment from an individual machine, which is on one computer, one CPU, one memory system, one network interface. A distributed system consists of many of these, right? And one of the fundamental challenges in distributed system is that you can't tell the difference between a slow node and a node that's completely down. It's non-deterministic. Now, we are engineers, and as the engineers, we take scientific academic results and we build technology using these principles, right? We're faced with challenges to which we can't find the answer on Stack Overflow. We have to take a principled approach. Here are some of the key foundational results in distributed systems that drive our software architecture, our guidelines. Every distributed systems engineer needs to be very, very intimately familiar with these results, and this is just the beginning. So one that I'll mention just a few of them. The first one is impossibility of distributed consensus with one faulty process. This is a result which basically says what I said earlier, is that when you have a distributed system and you're performing an operation involving multiple nodes, if it's possible for one of these nodes to fail, then the algorithm is non-deterministic, right? So it's basically saying distributed consensus is impossible. Now, of course, we are all used to the fact that consensus is indeed possible, right? And there is a different result, the consensus algorithm called Paxos, some of you might be familiar with. So this algorithm says, no, we could reach consensus. However, it doesn't change the foundational result because the way it's able to reach consensus is through elaborate uses of timeouts. It doesn't actually solve the underlying physical problem that distributed systems are asynchronous and independent things fail independently. Now, and this goes on. Another important result is linearizability. So linearizability is a correctness condition that must be used in a distributed system when you have more than one node, when you have replicas of data. How do you model the consistency of this data, right? And there's a term that's used very loosely in this community, which is eventual consistency, right? That's not actually a proper term because that's sort of saying like, well, we don't know. Eventually something happens. But there's a whole zoo of consistency models in between, the strongest one being linearizability, and then eventual consistency all the way on the other end. But there's things in between that you can take advantage of to solve a particular problem. Safety and liveness properties is understanding the difference between a safety property, which means that nothing wrong happens, versus a liveness property, which means something will eventually happen, right? We have to balance this idea of being always available while offering a consistent experience. Of course, we have to do both in this industry. We have to be 100% available. We have to be 100% consistent. And so to do that, we use these techniques. So the thing I want to talk about is something I call operations-driven design, right? There's all these different design methodologies, all these architectural styles. This is another one, right? But this approach is based on data. It's a data-driven approach to architecture and design. And this is a screenshot, actually, of one of our dashboards that we use to monitor the system, right? And this is just a tiny portion of the dashboard, but you have to be prepared to monitor systems like this using aggregated data in order to operate a large distributed system, right? We can't log into each individual machine and see what's going on. Moreover, there's a whole bunch of services involved in even a simple interaction on the platform, and we have to be able to monitor them. So, as I said earlier, we talk about providing a service, building services. So what is a service? Well, it's very simple in my view. A service is a program. We're computer programmers, we build programs, but there's more to a service. A service is also an SLA, a service level agreement, which discusses the reliability properties of this service. So let's break that down a little bit. SLA, behind the scenes, there's a few more terms. SLI is a service level indicator, which is sort of like a metric that you use to monitor the service. Service level objective is where the expected range of a metric is. And then SLA is the broader term that discusses what happens when we violate the SLA. How do we react to it? What is our on-call rotation policy look like? How long does it take us to repair these issues? And so a very common question I ask during interviews, including engineers and product managers, I ask them to think about the kinds of metrics they would want to monitor on a system in order to get a sense of how well it operates. So here's a quick example: throughput, how many requests are we processing in a certain time? Latency, what's the latency distribution? And it's important to use a robust statistic. Averages don't work for reporting latency. Error rate is a very important one. A very important metric in a distributed system is lag, right? If we have asynchronous processing, that means things are happening independently, and that means that we have to track them independently. And if you publish an event and another system is supposed to react to that event, well, there's a lag between when the event is emitted and when it's handled. You have to monitor that, because once it gets too big, things are going to break. So we talked about what an SLA is, SLI, SLO, and that a service is a program plus an SLA. And I'll just talk about a few design techniques that we have to keep in mind to build this sort of reliable, mission-critical piece of infrastructure, right? And so the first thing, distributed tracing, the broader term is instrumentation. We have to make sure that all of our code is instrumented, the services that we use are instrumented, and we're able to index, search, and report on that data. There's just no operating a system like this without being able to monitor it efficiently, effectively. There's a special query language that we use to query this monitoring data, and that's part of the work. Isolation, workload isolation. This is about thinking about the boundaries of your system, right? And you could think about the boundaries on the whiteboard, but the production workloads will tell you the real boundaries, right? There's no amount of architecting that's going to allow you to foresee what's actually going to happen in production. So in production, you have to be able to determine your boundaries based on what's happening in production. Sometimes you want to isolate your Tier 1 API from your Tier 2 API. And so this is where isolation comes in. This third one is a very, very important one. And there's a very, very common problem that pretty much every architecture runs into. Every internet-based service architecture usually involves persistence into a database and then the publication of an event corresponding to that change. And the vast majority of systems I've seen, they do this wrong. They do this completely wrong because they have the dual write problem, which is that you write into the database and then you publish an event, which most of the time that works fine, right? But we actually had a question earlier in this conference, is that what happens if there's an error in between, right? If there's an error in between persisting to the database and publishing an event, well, in a mission-critical system, this could be a disaster, because that is an inconsistency. You have one database that says the data is this, you have another one that says it's something else. And that's a huge problem. We can't just ignore it in a mission-critical system. We have to solve it. Right? And one solution to this sort of problem from back in the day is using transactions. If we're all on SQL Server and we have one table representing the state, another table representing the queue, well, great. Then we could actually open up a transaction and make sure that operation is atomic. But we're not using SQL Server, and we're not using SQL Server for everything. Just to give you a sense, we're on Azure, we're using Cosmos DB, we're using all the Azure services. And so how do we address this problem? This is another interview question that I ask, is that here's a problem, you need to write into the source of truth and a search index to denormalize. How are you going to solve the dual write issue? Well, one of the solutions that emerged over the past 10, 20 years, it could be called log-based orchestration or log-centric architecture. Event sourcing is another name for it. But event sourcing isn't just about using Kafka. Kafka alone won't solve this problem because Kafka is not the source of truth, right? The nice thing for us is that we're on Azure and we have access to Cosmos. Cosmos has something called the change feed, which effectively gives you access to the log. And so whenever we make an update in Cosmos, the change feed emits that event, and you could subscribe to it as if it were a Kafka. And so Cosmos combines the idea of storage and the publication and distribution of events. That's really the only way to address this dual write problem, but it's not even the entire solution to this dual write problem. There's other aspects of it I won't get into, but this is very much a core piece of the architecture that we have to have in order to operate a reliable system. Another set of techniques for operating a distributed system are all the various control policies that you have on the operations, on the resources. So here's some examples, right? So the most basic thing you can do is you retry, right? And so one of the paradigms we've had for building distributed systems that sort of Google championed is the idea of building reliable systems on top of unreliable components. So how do you do that? Well, one of the things you do is you replicate. You have multiple copies of the thing, and then if one of them fails, you retry with another one, right? So retries are a technique in operating a distributed system. Bulkhead isolation. This is a different technique where, let's say you have a dependency on a third-party service, and let's say that service goes down. Well, you could just kind of wait it out and see what happens, but sometimes you need to block it off and replace it with another service. You need to isolate. Sometimes it's better to disable it completely than having users wait and wait and wait. So isolation is another technique. Circuit breakers, similar. Timeouts. Timeouts are very, very important in a distributed system because asynchronous operations are non-deterministic. You don't know when they're going to complete. Sometimes you have to make it deterministic by imposing a timeout to say, okay, well, if it doesn't get done in 10 seconds, then we're quitting. All right? So you have to do timeouts properly, and it's not just about specifying a timeout. You have to look at the sequence of timeouts across front end and back end and all the dependencies, and they have to align together in order to do the proper timeout. Now, moving on, when things really get serious, right? When things really get serious, you're going to want to go multi-regional, right? So we are on Azure, and Azure is always been replicated within a data center. But in some cases, you want multi-region availability. Not just because the region might fail, it could also be that the code in this region is malfunctioning, and you might want to fail over to another region. Now, multi-region replication, that's a whole other story, right? You guys might know about Kafka, right? It's a very, very powerful system, but it doesn't support geo-replication. That's a much more complicated thing than just local in-data center replication. But in a large distributed system, you have to be able to operate across regions. Another set of techniques is about the release process, right? We have a really, really big system. We're constantly making changes to that system. One of the important tools in making that possible is feature flagging, where rather than releasing a feature to all the users and seeing what happens, we're able to pinpoint the feature to a specific user, collect data, see how it works, and then release it more broadly from there. This is sometimes also called canary in the coal mine. You're just making a release to a small portion of users, small portion of traffic, looking at the data, seeing what happens. Another technique in operating these sorts of systems. Moving on. So here are more guidelines. And by the way, I'm basically copying these from our internal documentation. Here are guidelines pertaining to input-output, right? So one of the things that's happened over the past 20 years in the programming model world is that we're all used to doing parallel and concurrent programming right now, right? We've all been told to do non-blocking I/O. And you have to do non-blocking I/O in order to take full advantage of the system. right? So the slogan is async all the way. All the way down to the root, you have to use non-blocking asynchronous code. As I said earlier, cancellation timeouts. Right, so some of you guys in the .NET world in C#, you might have seen this thing called a cancellation token, but you probably never really used it, right? Well, you have to use it. You have to use it in a large distributed system because otherwise you might have processes that are orphaned, that aren't attached to a user waiting for a response, but they're still running and consuming resources because the cancellation wasn't made when it was supposed to be made. One of the key optimization techniques in a distributed system is batching, right? So if you're deciding what an API looks like, sure, you should think about the functionality, but you should also think about the fact that there's a huge cost to moving data from one node to another. It's orders of magnitude more costly to move data across nodes than performing local operations. And so you have to architect your code and your system around the ability to batch to amortize round-trip costs. Pooling. Pooling is another technique that is only called for when you're really at maximum load. You never have to think about pooling if you're not going to expect some serious load on your system. Resource pooling. Pooling all sorts of resources. Sockets, memory buffers, all those things. If you're going to ask the computer to keep giving you new sockets every time you need one, well, eventually it's going to start to degrade in performance. So the technique is to pool them, right? And there's a lot of built-in tools that do this. In some cases, you have to take that into account yourself, right? We've already talked about control policies, retries, exponential backoff, and that's another important point, is that even designing a retries can be challenging, right? Because if you retry too much, you might get what's called a thundering herd, and all the machines retrying will actually take the service down. So you have to have exponential backoff. Parallelization, of course, is another strategy. Because I/O takes a long time, it's best to parallelize. Database guidelines. We already talked about some of the constraints around data. How do you choose a database? And the thing to keep in mind is to decouple the logical relationships in the data from the operational relationships and the modalities involved. Now I'll explain what that is. So the logical relationships are what you get from a relational model, right? Is that you might have a load, it has an asset, it has a customer, and these things are related, right? The operational model, it talks about how user actions and how events update the system state, right? So it's a different perspective that involves the relationship, but it's a different angle on it. Modalities refer to, like for example, eventually is a modality, right? Always is a different type of modality. And the point being that some things we need to be strictly consistent, some things could wait a little bit. There's different modalities involved. And for example, SQL Server or Oracle, they are limited in the modalities that they offer because they usually offer either synchronous or not at all, right? If you have an index in Oracle, well, it's going to get updated right away with each transaction. You can't do it later when the load is less, right? Understanding the consistency guarantees of a database, right? There's different consistency guarantees. Data is replicated, so it takes effort to bring it into consistency. And there's different strategies of full consistency, partial consistency. The strict names on Cosmos is strong consistency, session level consistency, bounded staleness, and then they do have eventual consistency all the way on the other end. Being able to denormalize your data around the access patterns, right? The logical relationships are one thing. The operational relationships will tell you what the access patterns are. How's this data being accessed? And then caching, just don't do caching. And that's all.
Thank you. And Leo, thanks for the awesome performance. And I think we have the time for one question. So if you have a question. Today we have a very shy audience. I was thinking I will try throwing something into them to wake them up a little bit.
Yeah.
My question will be about replication among different regions. What will happen to data if the connection between regions is lost?
Well, if the connection between regions is lost, then the replication stops, right? And so there's a lot that goes into understanding what happens to the data. Because let's say you have a primary region and a secondary region. Well, the multi-region replication works through what's called chain replication, which means that the writes go into the primary region and then they're streamed down to downstream regions. And so it's depending on the kind of failure that happens, but for example, if the connection is lost between primary and secondary, well, the replication stops, but because the events are handled in the same order, when it comes back online, it's able to continue applying this log in the same order, and so the system will be behind, but it'll be consistent. Right? So, and that's only some of the challenges involved in building this geo-replication protocol. Good thing we don't have to do it, because actually in my previous company, we were doing this event sourcing thing at scale, and we had to build our own multi-regional replication protocol where we had to think about things like this, and I'm very glad we don't have to anymore.
Yeah, one more quick question, because it came from online, so I want people to be satisfied online as well. So is Prometheus still the go-to for metrics? Are its paid alternatives such as Elastic APM and like worth it? Sorry.
I'm sorry. What's?
Yeah, you can read the question. Yeah, because maybe.
Oh, Prometheus. Okay. Yeah.
Prometheus.
So Prometheus.
Sorry. Yeah.
Prometheus is this tool for storing and reporting on metrics, and it's a very, very specialized tool designed for high scale. It's very, very lightweight metrics, and we don't use it. We're on Azure. Azure gives all these things to us as part of the package. But I did use Prometheus back in the day in the e-commerce world, and it was a good tool. But there's much more to instrumentation than just metrics. There's logs, metrics, and distributed tracing. They all have to work together.
Yeah, thank you very much. Thank you very much.